Welcome back to ECE 442-542. Not sure you can hear me in class just yet. The level was a little bit raised, but it's now down, I guess, to a reasonable level. The passport assignment is due Sunday, and there is no class on Monday. I hope you're aware of that. We have no class today on screens 4 and 8, if you were wondering why. Those are not working today, but I hope that if you're at home playing along, you can see what's on the screen that's being captured. For those that are playing along at home, the online students, you have a couple of options to take your exams. One, and the preferred option is through Examity, and the other is through a proctor. And I know that in the TCEs, you may not think that I read the teacher course evaluations, but one of the on-campus students last semester felt like they were not getting a fair shake because I gave the online students 24 hours to complete the exam. They only had a certain time window within that 24 hours, so they had the same 50-minute time slot to work the exam if they were online. They didn't have the entire day and 2 hours to complete the exam that the on-campus students were taking in 50 minutes. So hopefully the on-campus students realize you're not playing at a disadvantage with the online students. It's just that they can submit their exams in a particular 24-hour window, but they only have the same length of time that you have, which in this class will be 75 minutes. Our exams will be the entire period that we have here. To get you ready for the exams, homework number 1 is due on the 28th of January. There is now Z-transform material or references in Unit 2 on D2L, and you can start looking at those. That will actually be what we start talking about in Unit 2 as Z-transforms, and our exam will be due or will occur on Wednesday, the 6th of February, and that will be on us before we know it. Today, you may think, wow, we have a lot of goals, and I do have quite a few things to get through, but I'm including actually some information in those goals so that you're thinking ahead or your mind is locked into where we will be going. First, we'll review what we talked about last time, which is the solution to homogeneous linear difference equations. We'll expand that to solving non-homogeneous or forced linear difference equations. And if you want some additional material, you might look in sections Chapter 1.5 and Chapter 2.2 in DTSF. That's the Discrete Time System Foundation notes or write-up. We'll then talk about settling time for stable. If we have an unstable system, our system is not going to settle, but we can speak of a settling time for a stable system, and we'll do that for discrete time systems. And you have to kind of ask or figure out what is being asked. If I say how many sample periods, then I'm asking for capital N sub S in terms of settling time. Or I may actually want the absolute time interval. If that's the case, then you simply multiply capital N sub S by the sample period t to obtain the actual or absolute time interval t sub s, capital T sub s, which is the settling time. And here's a picture. Like I said, the goals are including some content. Here's a picture of an exponential response and what we mean by a 1% settling time. We have a tube, I'll call it a 1% tube, that when we get in there and never exit there as far as our response is concerned, the first sample that we reach that tube and stay in there is what we will call our settling time. That's N sub S, and if we multiply it by t, that would be our absolute time interval or the actual time interval T sub s, which is N sub st. And I've illustrated it for an exponential decay, but if it was a oscillatory, if it was stable and it was decaying, you could still imagine that response reaching a 1% tube. By the 1% tube, I meaning 0.01 times where you begin. If your initial condition is y at 0, you're looking to find when is my response going to be 1% of where I started, and I don't exit that tube. You could see that if I extended that red dashed line to the left, I'm entering that tube a lot, but I don't remain in that tube. So it's when you the first time you enter that 1% tube and remain in that tube. I hope that's clear. That's the settling time. Relative to settling time or response behavior, just make sure when you're working homework number 1, problem number 4, that you pay attention to the difference between parts A and B. They have different setups. They have different inputs and initial conditions. In part A, you're given maybe an input of 10 and no initial conditions. In part B, I've indicated here, you don't have an input, but you do have an initial condition of 1. So when you're reading or working that problem, make sure that you're keeping track that the setup, the inputs and initial conditions for the two parts are different. They're not the same. And that really has some connection to what I was talking about with settling time before. Here's where we're going. Maybe we won't get through all of this today, but this is where we will get to. We want to talk about discrete time block diagrams. There's material in DTSF dealing with block diagrams, section 4 of chapters 1 and 2. We'll look at time domain block diagrams. We'll call those all delay block diagrams. And those will lead to a state space representation. We could look at those similar diagrams in the frequency domain, where now our time domain delay blocks can be replaced by operators z to the minus 1. That now means that we're in the frequency domain, and we can find the transfer function description of our system by doing some block diagram analysis on that block diagram. So we'll talk more about state space representations, block diagram algebra. We'll then start worrying about how do we interpret this complex variable z. Z is a complex number, and to get maybe a feel for what it does in the time domain or what it corresponds to, if our characteristic equation has roots equaling z of some complex number, how do we interpret that in terms of its time response evolution? So that's how do we interpret this complex variable z as an operator. Z is an advance, z inverse or z to the minus 1 is a unit delay. So we can interpret this z many different ways. We will then talk about going back and forth between two different complex planes. We'll have a complex S plane and a complex Z plane, and we'll show that once we understand what Z looks like relative to S, that stability in the S domain, which is the entire left-hand side of the complex S plane, corresponds to the inside of the unit circle in the Z plane. We'll see that when we talk about this mapping between the S plane into the Z plane. We will also start talking about sampling frequency, and there's all sorts of frequencies to think about. We have omega, which has units of radians per sample, or radians per second. Then we have F sub s, the sampling frequency in hertz, which has units of samples per second or cycles per second. 2 pi is this conversion factor between those two frequencies. And if I start saying, oh, we have a sample frequency, hopefully you'll know, or it'll be clear from context, whether we're dealing with an omega or an F, whether we're dealing with radians per second or samples per second. And the sampling frequency, f sub s, is related to the sample period, capital T, which is how many seconds per sample elapses between the sampling operation. Capital T is then so many seconds per sample. And here's a rule of thumb. So if you want to write this on your thumb, that's okay, but it'll probably be on your crib sheet. The rule of thumb that we will sort of live with this semester is we will say, let's sample omega sub s 30 times the closed loop bandwidth. Omega sub c might be how fast we want our system to behave. Maybe we want it to operate at 5 radians per second. Maybe that's omega sub c. Then we would want to sample that, or we would want our omega sub s to be 30 times that. And that's just a rule of thumb. But that's something to sort of guide us in how do we select the sampling frequency. And you can hopefully see that once we have omega, we can find f or we can find t. And how we find omega is based on what our system dynamics will be in the closed loop setting. Let's now review, get ourselves mentally around where we left off, which was dealing with difference equations. And in particular, here we have a second order linear difference equation. It has no external input. Nothing is driving it or forcing it. It's just going to be responding to initial conditions. We then assumed the homogeneous solution, which is x sub lowercase h of n. That's what we will refer to as our homogeneous solution. We assumed a structure, a z to the n, and we're now trying to find those coefficients or those constants, a's and z's. That led us then, by substituting or replacing that structure into our homogeneous difference equation, it led us to this characteristic equation that the values of z needed to satisfy. We can see that the roots of that are now at z equal to -1 and z equal to -2. And once we have the roots, now we have the structure of our homogeneous solution. And on an exam, if I just ask you for the structure, I'm not asking you to find a sub 1 and a sub 2. I'm just asking you to find the z's, but then put it into something like this and say, oh, the solution structure would be some coefficient times -1 to the n, plus another coefficient times -2 to the n. And if you had another z value, if you had a cubic and it was 1/2, you would say plus another constant times 1/2 to the n. If I ask just for the structure, don't get carried away and go chasing off and finding all of the coefficients, the a1, a2, a3, unless I say I want the complete solution, closed form solution, which we can do here. Since we were given initial conditions, we use those initial conditions with this solution structure. We have 2 initial conditions. That now gives rise to 2 equations, and we have 2 unknowns, 2 unknown coefficients, a sub 1 and a sub 2. That gives us now these 2 equations, and you pick your favorite solution strategy. You could solve one of those equations solve for one of the variables in one of the equations and back substitute it into the other equation, or if you think in terms of matrices all the time, you just put it into a matrix and now you have ax equal b, where the x is now the a1 and a2. We have 2 equations and 2 unknowns. We simply invert that matrix, and I wanted to just illustrate that hopefully we obtain the same coefficients that we obtained last time, maybe solving with a different strategy. Here the a sub 1 ends up being minus 1, and the a sub 2 ends up being 2. And that is the closed form solution. It's more than just the structure. It's the closed form solution. Then we closed out the class last time by looking at the behavior of x of n, and we can find that by evaluating that complete solution for different values of little n. X of 0 was given, so we can check our work and say, oh, we do get 1, and that was what we were actually given as an initial condition, so that's good. X of 1 ended up being minus 3, x of 2 is 7, x of 3 is minus 15, and you could actually plug in any n that you want since we have a closed form solution. Suppose we plug in 10. Since we're electrical engineers, maybe we remember powers of 2. 2 to the 10 is now 1024, and that now gives us a value of x 10 samples in from the initial condition at 2047. We started at 1, and in 10 samples we're up to 2000. And if we were all lucky, that would be our bank account, right? We would put in $1, and in 10 months, let's say, it was up to $2,000. Then we could retire early, right? But you know how to work these problems. All right, now let's engage the class. I started with an initial condition of 1 at time 0, and was the response bounded or is it going unbounded? So hopefully you can see that it's going unbounded for a given initial condition, and that now says that this particular system is unstable. And we could have guessed that or known that if we simply reminded ourselves, as we will learn in subsequent lectures, that we can figure out stability of these systems by looking at where the poles are located in these transform expressions for a system response. In this case, our system had poles at minus 1 and minus 2. Those were the characteristic values, or those were the values of z that solved that characteristic equation. And you can see that one of those is right on the stability boundary and another is outside the unit circle, and that minus 2 is what's giving rise to this unbounded, and since it's minus, it's causing this bouncing back and forth between a positive and then a negative and a positive, but it's growing as it evolves in time. Any questions on that review? That should be getting us now back up to speed and ready to go into the non-homogeneous linear difference equation, and to make the transition maybe smoother, let's go ahead and just keep the same underlying difference equation, but now let's drive it or force it with a input that now looks like 1/2 to the n. Or now our forcing function our external input, let's say u sub f of n, is now 1/2 to the n. And do you want me to really get you confused? I could say u of n. What? So this you might see where now they're using this like a unit step, or that's now basically a switch that only turns that 1/2 to the n functional form on for non-negative values of n. Or you might want to see it or write it as 1/2 to the n for n greater than or equal to 0. So you may see it written many different ways, and that's where you might get confused. You go, well, I thought my input was u. Now you're using u as a unit step. Just when we're moving back and forth between different sources of information, you might see something like this, and now you just have to reflect back and say, okay, what is u of n? Are they using it as the input, or is it now the unit step? In this particular equation, I have u sub f as my forcing function, or my externally applied input, and u of n is the unit step. The nice thing about using this particular example is we already know what the homogeneous solution is. We've just done it. That was in our review. But if you were doing this from scratch, if this wasn't the same, you would first want to find the homogeneous solution. You would set the forcing terms to 0 and say, okay, what values of z solve the characteristic equation and give me the structure of my homogeneous solution. In our case, let me just write it down, just so that we sort of keep track of the process. This is now associated with our 0 input solution. We can say, oh, x sub h of n is now a1 minus 1 to the n plus a sub 2 minus 2 to the n. And that's coming to us from before. I didn't just pull that out of the hat. We know where that came from. That's our homogeneous solution by setting the right-hand side in this particular example to 0 and solving for the values of z that cause that characteristic equation to be satisfied, or to solve the characteristic equation. What we have to do now, if we're looking for a non-homogeneous solution, we don't now find the a1 and the a2. We wait. We wait on those until we found the particular solution. We'll add those, homogeneous and particular, together, and then we'll find the coefficients a1 and a2. As a word of caution then, don't solve for a sub 1 and a sub 2 just yet. Let's say don't solve for a1 and a2 until we find the structure of the complete solution. And the complete solution will involve the combination of the homogeneous with the particular. And the particular solution is going to be found from the forced difference equation. Like we did with the homogeneous, we actually assume a structure for the particular. And the structure that we assume, it's going to look like the structure that we're using to force the system. Unless we have a characteristic root having the same structure, then we have to modify it by n or powers of n. But in this case, what was our forcing function structure? What did it look like? It's now 1/2 to the n. Do you see how you're sort of hitting this system? You're hitting it with 1/2. One step later, initially you're hitting it with what? U sub f of 0 is 1. Then at time step 1, you hit it with 1/2. Time step 2, 1/4. Do you see how it's exponentially decaying? But that's now an exponential response or waveform in discrete time. 1/2 raised to the n. we now expect our particular solution to have a similar structure. Let's now just say, okay, our structure for the particular is going to be A3, A sub 3, 1/2 to the n, where this is the same structure as the forcing function. And what I was saying, let's say that in the homogeneous, maybe you had a z that was equal to 1/2, one of your values. And so the homogeneous might have had, let's say, an A4 1/2 to the n. Then we would have to get a linearly independent solution structure for the particular, or we would now say, oh, that means that a x sub p of n needs to be, let's say, a sub 5n 1/2 to the n. It needs to be linearly independent of what we would see from our homogeneous. We probably won't get that detailed in this class. It will usually, well, I shouldn't say that, but hopefully I'll design exam problems or homeworks such that we have unique particular structure and roots to the homogeneous difference equation. Now what do we do? Well, this was sort of an aside right here. What we want to do is now solve for a sub 3. We still haven't found a1 and a2. We'll find a sub 3 first. Let's now find a sub 3. And if that's our particular solution structure, that needs to satisfy our forced linear difference equation, and we know what that looks like. That's now x of n, but we're assuming x of n was a sub 3 1/2 to the n plus 3 times x of n minus 1. So that's now 3 a sub 3 1/2 to the n minus 1 plus 2 a sub 3 1/2 to the n minus 2, and that's equal to the driven or the forced difference equation, which was equal to 1/2 to the n. We now want to use this relationship to find a sub 3. That's the only unknown parameter in this. We can pick whatever n we want, but it's probably easier to just start with something simple. So let's now say with n equal to 0, we now have a sub 3 plus 3a sub 3 1/2 to the minus 1 plus 2a sub 3 1/2 to the minus 2 equaling 1/2 to the 0, which is 1. And if you plug in or multiply by 2 and then multiply by 4 effectively, or divide by those, you now end up with 15a sub 3 equaling 1. Or a sub 3 is now equal to 1/15. Or our particular solution, we now have a sub p of n is equal to 1/15 1/2 to the n. And our complete solution is the combination of our homogeneous and particular. Or we now have x of n is equal to a1 minus 1 to the n plus a sub 2 minus 2 to the n plus a sub 3, but we've already found that. That was 1 over 15, 1/2 to the n, and now we can solve for those unknown coefficients a1 and a2 using the initial conditions. We can now solve a1 and a sub 2 with the initial conditions. I need to give you something to do tonight. I know you want to do something when you get home, so you can solve that, and I'll give you the answer. I'll give you the answer in the back of the book, and if it's wrong, you can let me know. But I now came up with minus 2/3 minus 1 to the n plus 24 over 15 minus 2 to the n plus 1/15 1/2 to the n, and that's for n greater than or equal to 0. And if somebody now wants to find, and that was under the condition that x of minus 1 and x of 0, x of minus 1 was equal to 0 and x of 0 was equal to 1. If in fact that is x of n, what's the behavior of x of n as n gets large? What's x of n going to do? How is it going to behave? Can you tell from that expression? It's being forced now. Does that make a difference? The forcing term is going to exponentially decay, isn't it? But we still have these characteristic modes that are outside the unit circle, so this, for large values of n, is still going to go unbounded, this x of n. And you would expect that. We didn't change the characteristic property of that linear difference equation. We left it the same. It still had characteristic roots of minus 1 and minus 2. The behavior of x of n then for large n is still going to be unbounded, even though we kicked it with a exponentially decaying forcing function. All we have to do is excite that system, and you excite one of those unstable modes, which you have a mode at minus 2, and that's just going to go growing as n evolves, or as n gets larger. Questions on solving non-homogeneous linear difference equations? That should be similar to what you've done for differential equations. And now if you wanted to, you could now use this to solve differential equations if you could find a sampled version of that. Now you plug it in here and you're good to go. You have a strategy for solving linear difference equations. Let's look now at the next goal on our list, and that is to look at settling time for stable discrete time systems. With that setup, what's the settling time for x of n that we just finished? When does it settle? What value of n will be within 1% of where we started? Trick question, isn't it? It's not settling, it's unstable, it's unbounded, it doesn't have a settling time. So if somebody asks you that, you could say, oh, if they say, what's the settling time for this linear difference equation, you would say, I'm sorry, but it's not going to settle. There is no settling time. It's an unbounded response. So we have to have a stable system in order to even talk about a settling time. And just to maybe be different or to be consistent with earlier classes, depending on what you did in your class. I know last semester we didn't talk about 1% settling time. I think we talked about 2% settling time. So let's talk about 1% settling time in this class. We now have a 1% tube, not a 2% tube. So let's consider a 1% settling time. And to get a feel for how this works, let's go ahead and consider a particular initial condition response. Or we now are not going to have an externally applied input. Our input will be 0. And we're going to allow the initial value of our variable, let's call it y at time n equals 0, is going to be capital M. And we can gain the insight that we need by looking at a very simple system. Let's just look at a first order linear difference equation. And once we understand that, we can apply this same idea to any ordered system. So let's now look at a first order. And now we have y of n plus 1 is equal to a y of n. And to give us something to numerically think about, suppose that we let a be 0.887. With a equal to about 0.9, does that make sense to even talk about a settling time? Can we talk about a settling time now if a, this coefficient in our linear difference equation, is roughly 0.9? Yes, it's inside the unit circle. It's not that far inside, but it has a magnitude less than 1, so we know that as time evolves for an initial condition response, the value of y is just going to collapse. It's going to be a squared, a cubed, and that's just going to keep getting smaller since a is less than 1. What we want to do then is find the settling time. And I think I've just convinced you, you were shaking your head whether you believed me or not, but it's stable since the magnitude of a is less than 1. It could have been minus 0.887 and still it would be stable, but what would that produce? For a first order system with a equal to minus 0.9, what are you going to experience in your trajectory for y of n? It's going to go back and forth positive, but it will be collapsing as it shrinks in size, in magnitude. but it will be going positive, negative, positive, negative. In this case, we don't have such bouncing between positive and negative. We now have y at time 0. This is now y of n. Then we have at time 1, we're going to be a little bit less than 90% of where we started with y of 0. It's 0.88. Then at time step 2, we're going to be 90% of where we were at 1. And hopefully you see this decay. And what we want to know is at what little or what capital N do we eventually end up having a value of y of n less than that 1% tube, where this is now and we don't even have to include this one, but if it was popping back and forth, this would be minus 0.1 y of 0. What we're looking for now is this is some y at time sample period capital N sub s. We're trying to find the value for capital N sub s. Let's just think about this. If you were now asked this and you had to think your way through, well, you could start saying, well, I know that y of 1 is a y of 0. You're thinking in the background, but you're writing things down so that you kind of convince whoever you're talking to that you know what you're talking about. So I know that y of 1 is a y of 0. Y of 2 is a y of 1. That's the definition of the difference equation that we had. Y of n plus 1 is equal to a y of n. But now we can say, well, I know what y of 1 is. That's a y of 0. So I really have, in terms of my initial condition, y of 2 is a squared times that initial condition, y of 0. I don't think I need to show you this, but if we now did y of 3, we have a y of 2, and now we have a cubed y of 0. What I'm trying to do is convince myself of a pattern so that now y at some capital N is equal to what? I think I heard that even over the airwaves. We can do time travel. So even though you're watching this tonight at midnight, I heard your response. You said a raised to the capital N, y of 0. We have a connection. Or I hope you're connecting with what I'm trying to say. We now want to use this information, this insight, this solution basically to try to figure out what is our 1% settling time. That's what we're trying to capture. If we want a 1% settling time, what do we want y of n to equal? 1% of where we started. So this is now 0.01 y of 0 or less. So now we can use our relationship that we just derived. Y of capital N, we know we want that to be 0.01 y of 0, but we know that that's also a to the n y of 0. And here's the equation that we want to focus on, and y of 0 is common to both sides and it's non-zero, so we can divide both sides by y of 0, and now we have an even simpler relationship. Now we know that we're looking for the value of n that will be 0.01 or less. And if you had time, you could just start raising a to higher and higher powers. Guess, right? Guess and check. But you have another way of doing that. Since you're an engineer, you've had all of this math. What we want to do now is solve for n, where n is actually the number of time steps to settle to 1% of our initial value. And I know with this new math and the way that we're instructing you, you probably learned how to solve this in first or second grade. Did you get logarithms in second grade? Probably. With the new math? No? Somewhere maybe in your algebra background you learned about logarithms. You've used them now in engineering. If you've had 320, you've done Bode plots, and oh, we had logs in those, didn't we? Some of you are using logs right now. You need to wake up. Quit sawing those logs. But these logs are now log. Cha-ching, huh? Man. All right, so those of you at home, you can get away with sleeping, can't you? You just have to rewind and push play again after you've taken a 1-hour nap that you didn't plan on, but somebody's voice was driving you to sleep. So now let's take the log, and let's use base 10 because we're taking the log of 0.01, since that's a nice, or it's related nicely to a power of 10, since that's 10 to the minus 2. And that's now equal to the log, same base 10 of a to the n. And now we can use some of the rules for logarithms. Now we have a power. That power can now be multiplying. So now we have n log base 10 of a. Or we can now see that log base 10 of 10 to the minus 2 is minus 2. And that's equal to n log base 10 of a. And a was just a number, so we can find the log of that, base 10, and solve n by saying minus 2 divided by the log base 10 of a. And for those of you that brought your slide rule, you can calculate log of 0.887 on that slide rule. How many had to use a slide rule? Really? You're laughing at me? Okay, now you can use your calculator, I guess, apparently. I was just talking with an alum that graduated in 1957. Couple of hours ago. He had to come in and talk to somebody, so I was fortunate. Okay, don't give him the YouTube channel, please. But I wanted to ask him if when he transitioned from slide rule to calculator and then computers, but he was talking about playing with computers for the International Space Station and the Space Shuttle, so He had it going. I was impressed. But what's this give us? If we now take the log of 0.887, where were we? 1957. Some of you were still sleeping, right? If you compute that, you end up with n equal to 38.4 samples. Or now we can say the system transient will take approximately 38, but in terms of sample periods, what do we mean by approximately 38? That doesn't make any sense, does it? We have to have integer multiples. So in fact, we now have a system transient that takes 39 sample periods. Can we calculate the actual settling time, T sub s? And what does T sub s actually mean, or what's that correspond to? Since we were talking about time in 1957, maybe you think that was... He then accused me of placing him in 1857. No, I didn't say that. He goes, let's get in the right century now. Anyway, it was kind of fun. Where were we? T sub s. Can we find T sub s? The actual value. We have n. Do we have t? I didn't give you a t, did I? So let me give you a t just to use. Suppose the sample period was 40 milliseconds, or 0.04 seconds. So that now, if we wanted to, we could say, well, that looks kind of weird, so let me multiply 0.04 times 40 and then subtract 1, so that I now have 1.56 seconds. And this would then represent the real, or the absolute, time to settle, where this t is our sample period. That was the 0.04. That came out of thin air here, but maybe we'll have an example where we can see where a sample period of 40 milliseconds might make sense. But for here, that just sort of came out of nowhere, but just accept that so that now we can talk about 1.56 seconds. And how can you view 1.56 seconds? That's when the transient is gone. So essentially, that's like infinity, isn't it? So that's like if we were doing the final value theorem. Now, infinity just takes 1.56 seconds. So now you can go home and talk to your friends, colleagues, whoever you run into and say, when is 2 equal to infinity? And they're going to go, where have you been? And you'll say, well, it's Wednesday. And they'll go, what? Well, I just learned the settling time is 1.56, and that's effectively like infinite or infinity. Now people are really getting smart with this taking logs. They're sawing logs behind these whiteboards where I can't even see. Huh? Yeah, I don't have my glasses on, but I can still see those big white boards. Now I got you. All right. Any questions on this? Settling time. How would you find the settling time if somebody now said, oh, I have a system, and maybe they give you a z-plane sketch, and they say I have a pole here, and I have a pole here, and I have a pole here and here. This is in the z-plane. They're going to have to put some labels on it. Maybe they say here is 1 and here's -1. And you need to give them an answer on the back of an envelope, and they give you, okay, here are the roots of my characteristic equation. They live in these locations in the complex z-plane. What's the settling time? Or maybe they don't even say T sub s. What is N sub s? I think now you have the connection, right? Right now they may just say, how many samples will it take before we get within that 1% tube? Now what do? I don't know. Tharp just told me how to do it for 1x. Now I have 4 x's. How do I solve this? Can we talk about a dominant pole? I was going to try to draw a unit circle, but then I knew that I would be challenged to do such a thing. It wouldn't even look like an egg, but you can sort of imagine. You can get out your compass, since you've already got your slide rule working. We've got compasses now. There's the unit circle. Which of these, or any of these, dominant? Or how do we find, and what do I mean by a dominant pole? I've given you 4 poles, 4 roots of the characteristic equation, and now I'm introducing a new term, a dominant pole. Do any of those poles dominate the others? And what do I mean by a dominant pole? Any ideas? Any guesses? Pardon? You have 2 that are complex conjugates. How do I even know how those behave, right? We haven't even talked about that yet. But, oh, we have an answer? Really? I need to put my glasses. Oh, there. You're up against the wall. You blended in with a gray sweatshirt and a gray wall. Luckily, you have a pink hat. Or, I don't know. I'm sorry if I offended you. So now the comment from the side of the room was it's the pole that's the closest to the unit circle. And that's correct. It's really which of these, and actually they're all going to sing together. They're all going to play. They're all going to help. But in this class, we're just going to agree that we're going to find the pole that has the biggest R, the biggest magnitude. That allows us to deal with these complex conjugate poles. The pole that has the biggest magnitude, that's the one we're going to say dominates. Now that pole has to be inside the unit circle. If we have any pole outside the unit circle, we don't have a settling time. We can't talk about a settling time. Here, all 4 of those poles are inside the unit circle. I'm going to assume with my eyes that this one has the biggest R. I'm hoping that this distance, let's say R1, and this distance, R2, are less than R. That's what I'm assuming. And what's this distance? Well, these are supposed to be in conjugate pairs. This better be the same. It may not be sketched accurately, but if I have poles, they're going to occur in complex conjugate pairs. So those 2 complex poles are the same distance away from the origin. Here, we agree in this class that now essentially we have a y of n plus 1 equaling r y of n. And now we use that capital R like we used our A, and we can solve for N. Is that clear? We've now just gone from 1 to 4. If I went to 50 poles, you would just be looking at the magnitudes of those complex numbers. If any of those magnitudes are bigger than 1, you know that you have no settling time. If they're all inside the unit circle, you're looking for the magnitude of those 50 complex numbers that's closest to a magnitude of 1, and you'll use that for capital R. Yes? So now the question was, what if I heard you right, what if R sub 1 was equal to R? In this class, we're just going to go with the biggest one, and those two are equal. We'll just use R, capital R or little r sub 1, either one. In reality, they're going to sing together, and they're going to collapse it a little bit quicker than just what we're approximating with, but that's okay. For this class, back of the envelope, let's just say, let's look at R. This class will agree to use R, which is equal to little r sub 1. Does that answer your question? Other questions on settling time? Now you know how to compute the settling time or find infinity for a stable system. Let's now look at block diagrams, and in particular, block diagrams associated with difference equations. So now we're looking at all delay block diagrams, and let's assume that our difference equation is W of n plus 3 W of n minus 1 plus 2 W of n minus 2 is equal to R of n. And that should look familiar. It's exactly the same structure as what we've been playing with all along, but now what we want to do is actually create an all delay block diagram that would solve this difference equation if we plugged in an R of n and the initial conditions on the W's. And one way to do that is to first isolate the variable with the largest index. And in here our dependent variable is W, our independent variable is R. R is what we're adjusting, or that's our external input. Let's now solve for W of n. Or that's now R of n minus 3 W of n minus 1 minus 2 W of n minus 2. If you just had to guess, if you're now building an all delay block diagram, how many delay blocks would you guess there need to be in this delay block or in this diagram? How many times is W of n delayed? Twice. So we would expect 2 delay blocks generically. And now I'm changing terminology. 2 delay elements or 2 delay blocks. So let's now put in a delay block here and a delay block here. We're just going to say, okay, here's a unit delay. And there's another unit delay. And what if I injected into this leftmost unit delay, what if I injected into that W of n? what's going to come out the output of that unit delay if W of n is the input? W at time n minus 1. We now have coming out of here W of n minus 1. And now let's just go ahead and put that into the next delay block. And what comes out of the output of that unit delay? Same structure, same strategy. Here's now W of n minus 2. Now do you see how we can maybe interconnect this to make it look just like this difference equation for W of n? We have W of n on the leftmost side. Let's now make that be the output of a summing junction, where the inputs to that summing junction are the right-hand side of that difference equation. And we have most of those pieces. The only piece we don't have right now is R of n, but that's our independent variable. That's our external. We can create that. That we have. Meaning, let's now say, oh, W of n is what we need. It's made up of R of n with a plus sign. There's the first piece. I've already accounted for that. Now I know W of n minus 1 is right here. I just need to scale that with a minus 3 and have that as one of my terms. So now I've accounted for that. And finally, I have W of n minus 2 scaled by a minus 2. And now I've accounted for that. So now here is a all delay block diagram that is equivalent to that second order difference equation for W of n that we started with. Well, this is fun. Let's do another representation. Can we create a state space representation from this? Well, how are we going to do that? Well, here, let's create a state space representation from this all delay block diagram, and the strategy that we are going to use is as follows. The outputs of these delay blocks we will define as our state variables. Let me just write that down. What we want to do now is define the outputs of the delay blocks. We have two delay blocks, so we would be expecting to have two state variables. Define outputs of delay blocks as our state variable components. I don't follow. Well, here, let's follow what I'm trying to say. Here's the output of a state block right there. Let me call that one of my state variables, and I'll just call that x sub 1 of n. That's one of my state variable components. I have another delay block that has an output. Let me call that x sub 2 of n. And now I just need to find equations for x sub 1 at time n plus 1 in terms of my state variables and the input, and x sub 2 at time n plus 1 in terms of my state variables and R of n. And how will I do that? What's another way of labeling that particular line? We've already labeled it as W of n minus 1. You can actually virtually kind of eliminate or erase those W's now. Now we're trying to find a state space representation. That particular line I've labeled as x sub 2 of n, but what else is it equal to? Is it equal to anything else? Is it equivalent to something else? The output the output of that rightmost delay is x sub 1 of n, what's the input of that rightmost delay block? It must be the advanced version of x sub 1. So this is now x sub 1 of n plus 1. If the input to that rightmost delay is x sub 1 of n plus 1, its output is x sub 1 at n. What about this signal? How can I relabel that? This is now x sub 2 of n plus 1. Now I can start creating my state space representation, because what I want to do now is write x sub 1 of n plus 1 in terms of x sub 1 of n plus x sub 2 of n plus r of n. And I want to write x sub 2 of n plus 1 as something x sub 1 of n plus something x sub 2 of n plus something r of n. That will be my state space representation. Can we fill in those blanks? With respect to the top equation, x sub 1 of n plus 1, we scroll back and we say, okay, how can I rewrite x sub 1 of n plus 1 as a linear combination of x1, x2, and r? I now look at where that is as a signal. X sub 1 of n plus 1, what's that equal to? Do I see x sub 1 of n helping to form x sub 1 of n plus 1? Is there a summing junction with which x sub 1 of n plus 1 is an output? There could be, but there isn't, so it's really just one signal, and that one signal is x sub 2 of n. So really up here we have no direct connection with x1. We have a solid connection with x sub 2, and we have nothing with r. If we do the same thing for x sub 2 of n plus 1, now what do we have? Do we have a little bit more structure? X sub 2 of n plus 1, we do pick up r of n with just a 1. Do we pick up an x sub 1? Now we're just saying the output of that leftmost summing junction is x sub 2 of n plus 1. We now know that that's equal to all of the inputs going into that summing junction. It's minus 2 times x1 of n. It's minus 3 times x sub 2 of n, and it's 1 times r of n. And now we can write that even in a different form. We have this as two first-order difference equations. We can write that in matrix form. We can now fill in the 6 blanks, 6 element entries to those matrices, where this matrix, let's call it something else since we're in a different class. Let's call this, let's go Greek. Let's say it's phi. Let's say that is now our system matrix. Here is our input matrix, which let's call that gamma. And I hope you see that the size of phi is 2 by 2, and the size of gamma is 2 by 1. There's our 6 entries, and now we just need to fill in those entries based on the 2 equations above. We have nothing coming in or scaling x sub 1 of n. We have x sub 2 of n with a 1 and no r of n. The second equation gives us minus 2, minus 3, and a 1. What if I said I wanted an output, well, is it clear where the phi and the gamma came from? Now if I had an all delay block diagram that had 6 delay blocks, what would the phi matrix be dimensionally? How big would phi be if I had 6 delay blocks in my all delay block diagram? It's square, it's 6 by 6. If I had one input, gamma would be a column vector, a column matrix that's 6 rows tall and 1 column wide. And if we wanted to define an output, if we said the output y is actually x sub 2 of n, we could create the output matrix and the direct feed-through matrix to complete our state space representation. We'll pick up at that point after a break, so I guess I see you in a week, right? You don't have class on Monday. Our next class period will be next Wednesday. I'll see you then.